Welcome back to Java Internals Crashcasts. I'm Sheila, and with me as always is our Java expert, Victor. Today we're diving into the world of concurrent collections, specifically the concurrent linked queue. This is part of our chapter on concurrent list implementations, and we're excited to unpack this powerful tool for you.
That's right, Sheila. We've covered quite a bit in this season on concurrent collections, and the concurrent linked queue is a fascinating piece of the puzzle. It's a non-blocking concurrent queue that's designed for high concurrency scenarios.
Before we dive in, let's start with a quick quiz for our listeners. Here's the question. In a highly concurrent environment, which operation on a concurrent linked queue is typically faster? Adding elements or removing them?
Ooh, that's an interesting question, Sheila. It really gets to the heart of how this data structure works internally. I'm sure our listeners will have to think carefully about the concurrent nature of the queue and how that might affect different operations. But let's not give away too much. We'll reveal the answer at the end of the episode.
Absolutely, Victor. Now, to set the stage for our discussion, could you give us a quick overview of what a queue is in computer science and why we need a concurrent version?
Certainly, Sheila. A queue is a data structure that follows the first-in, first-out principle, or FIFO for short. Think of it like a line at a grocery store. The first person to join the line is the first one to be served. In computing, we use queues to manage tasks or data in a specific order. Now, when we talk about a concurrent queue, we're dealing with a queue that can be safely accessed and modified by multiple threads simultaneously. This is crucial in multi-threaded applications where different parts of the program need to add or remove items from the queue at the same time.
That makes sense. So the concurrent linked queue is Java's implementation of this concept. What makes it special compared to a regular linked queue?
The key difference is its non-blocking nature. Unlike synchronized collections that use locks to ensure thread safety, concurrent linked queue uses lock-free algorithms based on atomic operations. This means multiple threads can perform operations on the queue simultaneously without blocking each other, leading to better performance in high concurrency scenarios.
Fascinating. It's like a multi-lane highway for data, where cars, or in this case, threads, can merge in and exit without causing traffic jams. Can you explain a bit more about how it achieves this non-blocking behavior?
That's a great analogy, Sheila. The concurrent linked queue achieves this through clever use of compare and swap operations, or CAS for short. CAS is an atomic instruction provided by modern processors. Essentially, it allows the queue to make changes to its internal state in a way that's atomic, meaning it happens all at once from the perspective of other threads, without the need for locks.
I see. So it's using these low-level processor instructions to manage concurrency. That sounds complex. How does this translate to its internal structure?
The queue is built as a linked structure of nodes. Each node contains an item and a reference to the next node. The tricky part is managing the head and tail of the queue. When a thread wants to add or remove an element, it uses CAS operations to update these references atomically. If the KS operation fails because another thread made a change, it simply retries until it succeeds.
That's really clever. It reminds me of a story I heard about a large e-commerce platform that used concurrent linked queue to manage incoming orders during a flash sale. They were able to handle millions of concurrent requests without any data loss or significant slowdown. Is this a typical use case?
Absolutely, Sheila. That's a perfect example of where concurrent linked queue shines. And you're right, it is a typical use case. It's ideal for producer-consumer scenarios with high throughput requirements. Other common use cases include task scheduling systems, message passing between threads, and implementing caches.
Now, I'm curious about its performance characteristics. How does it compare to other concurrent collections we've discussed, like copy-on-write array list?
Great question. Concurrent linked queue offers better scalability in multi-threaded environments compared to collections like copy-on-write array list. While copy-on-write array list creates a new copy of the entire list for each write operation, concurrent linked queue only modifies the necessary nodes. This makes concurrent linked queue more efficient for frequent modifications, especially in scenarios with many threads.
That makes sense. Are there any downsides or limitations we should be aware of?
Yes, there are a few things to keep in mind. First, the sized method is not constant time. It has to traverse the entire queue to count elements. Also, it doesn't support null elements, which can sometimes catch developers off guard. Lastly, while it's very efficient for concurrent access, for single-threaded scenarios, a simple linked list might perform better due to less overhead.
Those are important points to remember. Now let's circle back to our quiz question. Victor, would you like to reveal the answer?
Certainly. The answer is that in a highly concurrent environment, adding elements, offering, to a concurrent linked queue is typically faster than removing them, polling. This is because adding only requires updating the tail of the queue, while removing needs to update the head and potentially help other threads complete their operations.
Thank you, Victor. To wrap up, let's summarize the key points about concurrent linked queue. First, it's a non-blocking concurrent implementation of a queue. Second, it uses chaos operations for thread safety, making it highly efficient in multi-threaded scenarios. Third, it's ideal for producer-consumer patterns and high-throughput applications. Fourth, it offers better scalability than copy-on-write collections for frequent modifications. And fifth, it has some limitations, like non-constant time size operations and no support for null elements. In our next episode, we'll be concluding our chapter on concurrent list implementations with a summary of what we've learned. Stay tuned.
Excellent summary, Sheila. I'd just like to add a quick tip for our listeners. When using concurrent linked queue, prefer the offer and poll methods over add chance, and remove. The former are optimized for concurrent use and don't throw exceptions, making your code cleaner and more efficient.
Great tip, Victor. And that brings us to the end of today's episode. Listeners, if you've enjoyed this deep dive into Java's concurrent collections, please subscribe to Java Internals Crashcasts and leave us a rating. Your support helps us continue bringing you these in-depth explorations of Java's internals. Until next time, keep coding.